Hi everyone, my name is Kisol Lee from Cornell University. Today I'm going to introduce SoNIC, software-defined network interface card, which allows users to access and control entire network protocol stack in real time and in software. This is a joint work with Wang and Professor Hakim Weatherspoon. So interpacket delay, which is defined as the timing difference between the first bit of two subsequent packets, has been widely used for network research for a very long time. For example, we can create a certain patterns of packets being generated, and we can use interpacket delays to capture and analyze packets that are captured. And we can use this information to characterize network components such as switches and routers, or even the network itself. Or you can even estimate available bandwidth of a network, or you can increase the throughput of TCP protocol by controlling interpacket gaps or interpacket delays, or we can create or detect or prevent any covert timing channels in the network. Here, we argue that we can improve all these network research applications with the access to the physical layer. How can you do it with the access to physical layer? Well, the answer is to the idle characters, which are special characters that only reside in the physical layer and thus not visible to higher layers. Idle characters basically fills any gaps between any Ethernet frames in the physical layer. In particular, the 10 gigabit Ethernet protocol requires two each end sent at 10 gigabit per second. And therefore, each bit is about 100 picosecond wide, and each idle character consists of 7 or 8 bits in the physical layer. And because 10 gigabit Ethernet always sends at 10 gigabit per second, either an Ethernet frame or the idle characters, if we can count the number of idle characters or the bits that make up the idle characters, we can perform very precise network measurements. So for example, if there are 12 idle characters, that means there are 100 bits between two frames, and that it can also be translated into 9.7 nanosecond. Therefore, by accessing and control every bit in the physical layer, we can achieve unheard level of precision and control, which can improve network research applications that I previously mentioned. And I'm going to go over these three applications in later of this talk. So our principle number one is the precision. Precision of network measurement can be significantly improved at sub-nanosecond resolution with the access to the physical layer. Then the next question you can ask is are there any ways already that support this kind of control and access to the idle characters? Well, the physical layer has been simply a black box to network systems researchers. There is no interface from the network interface card or from the operating system which allows you to just control these idle characters. So when these two packet streams arrive at the destination, there's no way to tell the difference between these two packet streams because all these idle characters are discarded before delivering this package up to higher layers. And second, we may be able to do so with specialized hardware such as customized ASIC chips. However, as network systems researchers, we want to do so in software, not in hardware. So the second principle here is software. We want to be able to control and access every bit in the physical layer, and we want to do so in software. In fact, we have done this before in our previous work called bifocals. We were able to access and control every bit or idle characters in the physical layer to achieve unprecedented level of precision. In particular, we use laser and modulator to create optical signals of the medium, and we use oscilloscope to capture those optical signals for offline analysis. And we use this tool to test against National Lambda Rail Network, and we discuss the results in our IMC 2010 paper. However, there are certain limitations of this tool, and first of all, and the most importantly, this tool is not a real-time tool. It requires a few thousand hours of CPU processing time, and it can only capture 2.0 microsecond worth of data at a time because of the small buffer installed into oscilloscope. And this tool is $500,000 tool, which is very expensive and not easy to deploy. So our last principle here is real time. We would want to achieve the same level of precision and control as in bifocals, but only in real time. So the goal here is control every bit and in software and in real time. And in order to do that, we need to access the physical layer in software. So for the rest of the talk, I'm going to introduce SoNIC, software-defined network interface card, and the applications that SoNIC enables. And the main idea of SoNIC is to implement all the functionality of the physical layer in software so that we can control and access every information in transit in the real time and in software. And we want to do so with the commodity component. And before I discuss the details of design and implementation of SoNIC, I will briefly go over the details of 10 gigabit Ethernet network protocol stack to help you understand the design decisions we made while we were implementing SoNIC. So from now on, I need to pay close attention at least for 30 seconds because I will go into the very details of the physical layer of 10 gigabit Ethernet protocol stack. And most of this information you may already know, but some you may not. And we know that when application generate a packet, transport layer and network layer add their own headers to the packet payload, and data link layer does the same thing. And not only that, but the data link also prepends preamble in the front of the packet, and it inserts a cyclic redundancy check value, which is used to detect bit corruptions at the receiving end at the end of the packet. And lastly, the data link layer inserts at least 12 idle characters or 96 bits at the end of the Ethernet frame. And from the data link layer to the physical layer encodes an Ethernet frame and idle characters into 64-bit blocks. And it also adds 2-bit sync headers to every 64-bit block. So the actual data rate of the 10 gigabit Ethernet protocol is not 10 gigabit per second, rather it is 10.3125 gigabit per second. And that scrambler takes each block and scrambles each bit to maintain the equal number of zeros and ones in transit. And we call it this balance. And the gearbox then takes every 16 bits from each block and delivers them down to the lower layer of the physical layer. The PMA, or the physical medium attachment sublayer, then takes those blocks and serializes them into one single bit stream. And then lastly, the physical medium dependent sublayer takes those digital bits and converts them to optical signals and transmits of the physical medium. Then the question is, where are idle characters? Where the idle characters are now embedded into some of the blocks while the physical layer encodes an Ethernet frame. And normally, the commodity network interface card usually puts the boundary between the hardware and software somewhere within the data link layer. And because of that, the idle characters between these two packets can be discarded before delivering those packets of the higher layers. And the interpacket delays can be significantly perturbed because of the network stack overhead. So our goal is to push the boundary between the software and hardware somewhere within the physical layer so that we can keep the information, such as idle characters, in software. And as a comparison, NetFPGA, a network research platform, tries to implement as many functionalities in hardware, which is exactly the opposite direction of SoNIC. So our approach of designing SoNIC is to separate what is sent in software and how it is sent in hardware. So the main idea is that we are trying to implement all the functionality of the physical layer that do not manipulate any bits or modify bits in hardware, and all the functionalities that manipulate or touch modified bits in software. So the lower part of the physical layer, such as physical medium attachment layer or physical medium dependent layers, can be implemented hardware, while others must be implemented software. So this is the overall architecture of SoNIC. And I'm going to details of hardware and software components of SoNIC in following slides. So first of all, we are using a very high-end FPGA development board for SoNIC hardware component. In particular, we are using these two small form factor pluggables, which is in red box, which is basically where the optical fibers are plugged. And in purple box, which is an FPGA chip, then deserialize those bit streams from the optical signals and delivers them to host memory via a PCI generation 2 interface, which can support up to 32 gigabit per second. And then, in order to implement software components of the SoNIC, we are using a lot of dedicated kernel threads, and they are pinned to their own individual CPU cores to utilize CPU at maximum speed. In particular, we are using 2 threads to implement the physical coding sublayer, and we are using 2 kernel threads to implement the data link layer. And then we take one of them and pipeline them together to implement the transmit path and the receive path. Not only that, but we also have an app thread, which is a specialized thread as an interface between the kernel space and the user space, and it can be used for customized functionality that user requires. So we are using at maximum 5 dedicated kernel threads to implement 1 physical core, and we can support up to 2 physical cores simultaneously. As I said, because all the functionalities that touch the bit in the transit are now implemented in software, we can control and access all those idle characters in software. And it is very important to process bitstream continuously, because this continuous bitstream means a broken link or lost packet. So we have to synchronize software and hardware or kernel threads very tightly. In order to do that, we are using low latency FIFOs to synchronize software components, and we are using pointer polling techniques to synchronize hardware and software. With this technique, we created a small data structure which is shared by software and hardware, and where only hardware can write. So software is basically pulling the values out of the data structure to find out when to start the next DMA transaction. This way is better than interrupt because there is no overhead associated with interrupt overhead routines. And this is better because the 10 gigabit Ethernet requires a continuous bit stream. That means there's always data to be transmitted between software and hardware. And this design was not enough. We had to do a lot of optimization to support real-time capability. We did a lot of optimizations on each functional block of our design. For example, a scrambler takes 59 bits to produce 1 single output bit. This is a very fine-grained state dependency, and it could easily become a bottleneck of the SoNIC design. And initially, this naive implementation of scrambler, which was used in bifocals, used a for loop which iterates over 64 bits of each block. And the throughput was not good, which was less than 1 gigabit per second. So we optimized this scrambler, completely removing for loop, and we reduced the number of bit operations, such as shift or extra operation, down so that we could achieve the high-performance scrambler. Not only that, we also did a lot of optimizations both in data link layer and the DMA engine, and they are discussed in the paper, and I'm not going to discuss in this talk. So SoNIC exposes an interface for user space applications, such as IOCTO system call for hardware control, and character device interface for communicating data in and out from the kernel space. And here is a sample C code for packet generation and packet capture of SoNIC. I'm not going into details of this source code, but what I'm going to tell you is about this small interface that allows users to control the interpacket gaps between packets in the number of idle characters. What is the significance of 12 here? That is the minimum number of idle characters required by the Ethernet standard to be injected between any Ethernet frames. So if we are injecting 12 idle characters, so we can achieve the maximum data rate. We can do a lot of interesting, flexible use of interpacket gaps with SoNIC. So for the rest of the talk, I'm going to discuss the applications that SoNIC enables. And before that, let me define interpacket delays and interpacket gaps again. Interpacket delay is the timing difference between the first bit of 2 subsequent packets, whereas interpacket gap is the timing difference between the last bit of 1 packet and the first bit of the second packet. Packet generation and capture are most basic functions for network research. With SoNIC, we can control interpacket gaps in the number of idle characters when you generate packets, and we can capture the number of bits within or between Ethernet frames when you capture packets. And for this evaluation, we are using a packet stream at 9 gigabit per second, where packet size is large MTU size packet, which is 1518 byte. So we are trying to generate packets with SoNIC with fine-grained control over interpacket gaps. This is how we generate packets with SoNIC. Here, x-axis is interpacket delays in nanosecond, and y-axis is CDF. And we validated what we generate with SoNIC with techniques very similar to bifocals using high precision oscilloscope or specialized hardware. And as you can see from here, SoNIC generates package with no variance. The interpacket delays between packets is always 13,992 bits. This is very uniform and no variance. On the other hand, for comparison, we also try to generate package with sniffer Tenji, which is a specialized network interface card which allows users to inject and capture packets at line speed. And as you can see from here, more than 80% of packets are generated with a minimum interpacket gap. And the variance was really higher than what expected. So takeaway here is that SoNIC allows precise control of interpacket gaps while generating packets. And then with this capability, we measure the capability of packet capture. We use the same packet stream at 9 gigabit per second. And the vertical gray bar here is what was generated with the uniform interpacket delays. And SoNIC can capture exactly what is sent. There's no variance here. On the other hand, other techniques like kernel timestamping or user space timestamping or sniffer Tenji timestamping cannot exactly capture what is sent. There is always a variance or the difference between the interpacket delays. So the takeaway here is that SoNIC can capture what is sent precisely. With these two cool capabilities of packet generation and packet capture, now we can create a Covert timing channel which is virtually impossible to be detected in higher layers. Here we are trying to embed signals into interpacket gaps. For example, you can embed signal 1 with large interpacket gap, and we can embed signal 0 with smaller interpacket gaps. And you are able to create a Covert timing channel by modulating interpacket gaps at 100 nanosecond scale. So in this evaluation, we created Covert timing channel over channel which was running at 3 gigabit per second. And the data rate of Covert channel was equal to the packets per second of the over channel because we can embed only one signal into one packet. And the data rate of Covert channel was about 250 kilobit per second. And we created a network topology as consists of three commercial switches that we don't have any control over. And we were able to achieve a bit error ratio less than 1%. Let me be more specific. In order to create a timing channel, at the receiving end, we considered interpacket gaps which is larger than 3,562 idle characters as signal 1, and less than that value is considered as signal 0. And in order to create that timing channel, we modulated interpacket gaps by adding or subtracting 128 idle characters, which is about 100 nanoseconds, to create the timing channel. And as you can see from here, when SoNIC is receiving packets, it can correctly recover the bit. Here we generated we were trying to embed the same number of zeros and ones to the over channel. As you can see from here, SoNIC is able to detect all the bits correctly. And the actual bit error ratio here was 0.37%. For comparison, we captured the same package with the kernel timestamping. And as you can see from this graph, kernel timestamp cannot detect this timing channel, nor detect the bits correctly at all. So the takeaway here is that by modulating interpacket gaps very precisely at 100 nanoscale, we can implement a Covert timing channel which is virtually impossible to be detected by any applications running in higher layers. So we developed SoNIC to achieve unprecedented access to the physical layer with commodity hardware components so that cross-network research can be possible. We carefully designed SoNIC, and we did a lot of optimizations to achieve precise or real-time software access to the physical layer. And we are currently integrating a SoNIC board into data center network and Genie test beds for large-scale measurements. And we are trying to scale up the SoNIC board to support the 40 gigabit Ethernet. So to conclude, we introduced SoNIC, software-defined network interface card, which allows users to control and access every bit in the physical layer in software in real time. And we discussed the applications that SoNIC can enable. So we have a demo tonight, so if you guys are interested, you can come and see us, and I'll take questions, and thank you very much.
Hi, Dong Soo-han from Carnegie Mellon. Thank you very much. Is there any limitation in the type of application that you can support? Because you seem to be sharing CPU resources for the application, as well as for the processing for lower level details?
Yes, so when a user is trying to develop an application that can run on top of SoNIC, the requirement is that the application itself has to perform faster than 10 gigabit per second, because each component of the SoNIC in kernel space and hardware is continuously running at 10 gigabit per second. If the software does not meet that speed, then application will fail to generate the package correctly.
Thank you.
Nikita Borisov, University of Illinois. It's very interesting that you were able to observe this timing channel, and if I understand correctly, you were able to see it over several hops, over several hops of routers.
Yes.
Does your experiments depend on the fact that the routers have no other cross traffic?
We are looking at that right now. For this evaluation, we are trying to just show that this is feasible, and we have to show that this is possible with this current setup. And we are now investigating over multiple commercial network by modulating interpacket gaps. But in this case, we have to modulate interpacket gaps more larger than this evaluation. Yes.
Thanks.
James Hong-Yi Zheng from Stanford University. Very good talk. I'm happy that you refer to the NetFPGA, because we help to build the NetFPGA. So I have two questions. The first question is that is the FPGA board you use is essential in your whole design? Can you use some other FPGA, or is there anything special about your hardware platform?
Also, the reason that we picked this FPGA board is that the FPGA chip is using a high-speed transceiver which is running at 11 gigabit per second. That's the requirement that we required, because the bitstream is coming at 10.31 gigabit, 10.3125 gigabit per second, and we didn't want to any physical chips to modify bits. But with this chip, it can receive those bit streams from the optical signals directly, not touching the bits with the high-speed transceiver. That's why we picked that board. So if you want an auto FPGA board for this functionality, then I would say that the FPGA must be using a transceiver that is faster than like 10.3125 gigabit per second.
Thank you. And the second question is, in your presentation, you showed a CDF about the interpacket gap, right? Mm-hmm. I'm wondering why there's still a CDF, because you use hardware platform. So what you see should be like just a straight line without any error. Can you tell us what kind of errors, what kind of causes, what kind of places that could cause these errors?
So when like a specialized hardware or kernel space user space tries to timestamp incoming packets, the moment that they timestamp the packet is not the same as the packet actually arrives at the destination. Because SoNIC is capturing the timestamping at the very lowest level, we can keep the interpacket delays not touched by any component of the host PC. But when you think about when kernel is timestamping a packet, there's a lot of overheads associated with the network protocol stack, interrupt, DMA transactions, and like system calling overheads, everything. So when you are timestamping a package at higher layers, the interpacket delays is already perturbed by the overheads.
So if you timestamp the packet on the hardware, then you can potentially eliminate these errors. Is that right?
Not really. In most cases, hardware is using an external clock to timestamp the package, which is running slower than the actual data rate of the 10 gigabits in the protocol. The main idea of ours is to use the timing base of each bit, not the external clock to timestamp incoming package. That's the difference.
Thank you.
Okay. Yes, that's great. Junda from Google. My understanding is that every port has at least 5 dedicated kernel threads. Is that right?
Yes.
And does it mean the 5 cores has to be used? Like otherwise, you have this interference between dedicated kernel threads.
Also, we basically pin each thread onto a physical CPU core, and we rerouted all the interrupts to other CPU cores.
Right, so that's 5 cores at least. Is that right?
Yes, but we are not using 5 cores. We are not using all of them every time. Depending on the application, we can use only 2 or 3 at the max. In worst case, we can use 5, yes. But
that's
the server we have had 12 available cores, so we were using all.
Yeah, my question is mostly about if you take like 80% of the cores of your server, and you have like 2 cores remaining for all the other applications. How do you handle the trade-off? It's like,
I mean, I guess it depends on how you use the server. I mean, in this evaluation, you are using the server only for these network evaluations. So,
but for the caption, and you have to write like 10 gigabit at least to store the data, right?
oh, to handle that, so we are not processing the incoming packets continuously because the overhead, I mean, if you receive those bitstreams and try to dump down to a file, it takes a lot of time and there's a lot of overload associated with it. So with this evaluation, we were trying to keep as much as data possible in the memory space first during the evaluation, then after that we dump down to a file system.
Okay, makes sense.
Thank you.
Thanks.